Hello everybody and welcome to our next video in Unit 7, which is using ice charts to determine equilibrium concentrations. So you might have already seen some charts that look like this, especially in the I do, we do, you do's. Like I mentioned recently, I think equilibrium starts to get a little bit easier once we take all of these minute topics that we've been talking about and really putting them all together. If you notice, this unit has a lot of different subunits to it, and they're not necessarily hard subunits, but we kind of have to learn each individual section in order to get the big picture for equilibrium. So we're knocking off a lot of different parts of Unit 7, and then we're really going to put it all together, and I think it'll make a little bit more sense. But anyway, so let's take a look at these two graphs over here. So both of these are concentration versus time. So we see concentration is here on your y-axis and time here is on the x-axis. Looks like here we can write an equation just by looking at this particular graph because we can tell what our reactants and products are. If I notice, it looks like oxygen, O2, and SO2 have to be my reactants. And that's because I'm starting off this reaction by decreasing in concentration. So those have to be my reactants. So I have SO2 plus O2 are my reactants. And my product must be SO3. And again, I know that because at a time of 0, I'm starting off with a concentration of 0. So that makes sense, SO3, right here. And we'll see that the slope of these lines where they start off are not the same, right? They're quite different, in fact. This line is very steep, as is this green line for SO2. And my O2 line is not as steep, but we can figure out what's the change in concentration. So let's try to color code this here. If I look at my initial concentration for O2, so I'm starting right off about here and going down to my equilibrium concentration, this difference is quite different from the difference from SO2. So if I look, I'm starting off right about here, and I'm going down quite a bit more to reach equilibrium. That was not a great example. It should be going down to about here a little bit more. And my SO3 is going, it looks like about the same amount as my SO2. So the change, I'm going all the way up here when I reach equilibrium to about equilibrium, down to about here. So it looks like this and this are equal, whereas this one is not. In fact, these two almost look double the amount. Why would these two be double the difference? Why would this difference right here, the concentration, be going down of SO2 as much as the concentration of SO3 is going up? Why is that twice the amount as O2? This comes down to concentration. This comes down to your balanced coefficients. So that must mean that SO3 and SO2 probably have the same coefficients. Looks like it has to be this right here. So I have 2 SO2s, 2 sulfurs, 2 sulfurs. Let's look at oxygen. 4 oxygens here, plus another 2 gives me 6. 2 groups of 2 gives me 6. The reason why this line and this line are 2 times that of this line here is because of that balanced chemical equation. The SO2 is being used up twice the amount as O2 is, and that's because every 2 SO2 molecules reacts with 1 O2. This one on the right, I don't think I like as much because I'm pretty sure that it's not, that they don't look like as nice as this one does. Like we can clearly see that the amount that my SO3 concentration increases is the same as the amount that my SO2 decreases, and that's because it's the same ratio. This one, it doesn't look as clear. What I wanted to show you though is that sometimes you might have a graph that looks like this, where I see that it looks like it's reached equilibrium at some point, but then I see this sharp increase that occurs at some point in time. This is because you would have more of some reactant or product that's added. And we're adding some sort of stress to that system. And when we're adding some sort of stress, the reaction is going to change in a way in order to relieve that stress. So if I look at this balanced chemical equation, if I add more nitrogen, right? So that's what we're doing here. I'm adding a little bit more nitrogen. I could make more NH3 from that. And we could see that once I add more N2, more nitrogen to this system, my amount of ammonia actually does go up because the equilibrium is shifting in a way to produce more product, because Q is not equal to K at that point. If I have more reactants, I can make more products. However, if I also have more reactant, that means that I'm going to have less of my other reactant because I need hydrogen to react with that nitrogen. So we could see here this hydrogen starts to go down a little bit. So once I add some sort of stress, and you'll see that represented with some sharp increase or a sharp decrease, you'll see that the equilibrium is adjusting in a way in order to relieve that stress. So those are just what different graphs will look like to represent the changes in concentration based on that balanced chemical equation. So let's take a look at sample problem 9 right here. So this one says carbon monoxide and hydrogen react according to the following equation. So when 1 mole of CO and 3 moles of H2 are placed in a 10-liter vessel at 927 degrees Celsius and allowed to reach equilibrium, we want to know, or it says, the mixture is found to contain 0.387 moles of water. What is the molar composition of the equilibrium mixture? So basically, we want to know how many moles of each reactant or product are present in that particular example. So it's not asking for the molarity, it's just asking for molar composition. So we're just going to keep this in units of moles to make it a little bit easier. So I'm going to rewrite this equation here. So carbon monoxide reacts with some hydrogen, and that's in equilibrium with methane and water. We're going to set up an ice chart, right? So I'm going to put ICE right here. I stands for initial. This would be the initial amount of moles, the initial concentration, whatever is given to us in the problem, or before equilibrium is established. And it says we have 1 mole of carbon monoxide and 3 moles of hydrogen, and it's allowed to come to equilibrium. So these are my initial amounts. I have 1 mole of CO and I have 3 moles of H2. I didn't put any methane or any water into this system initially, so that initial molar amount would be 0. We can then determine what is C, right? And C stands for the change in the system, change. And we can see what the change is by looking at that balanced chemical equation. We know that this reaction, based on how it is, has to go in the forward direction because I don't have any products here, right? Because there's no products, this has to first go in the forward direction. So therefore, I have to make some amount of products. How much product am I going to make? Well, some amount X, because we might not know right off the bat what it is, but this is going up some amount. Water is also increasing the same amount, and that's because this is a 1-to-1 mole ratio. So however many moles of methane is formed, we're going to form the exact same amount of water because they are in a 1-to-1 mole ratio. Of course, I'm using up my reactants in this case. So my amounts that my carbon monoxide is being used up, that's minus X. This has to be minus because it's losing some of its moles because it's making products, but it's also going to be the same exact absolute value as methane in water because this is also a 1-to-1 mole ratio. I'm using some number of moles to begin with, but whatever amount of CO is reacting, I'm forming the exact same number of moles of each product. My hydrogen, on the other hand, I'm using 3 times the amount of that. So I'm using up 3 molecules of H2 or 3 times the number of moles of hydrogen as I am everything else because I have 3 moles of hydrogen that react per every 1 mole of carbon monoxide. My equilibrium is what E stands for. So E stands for equilibrium. So my equilibrium amount would be 1.000 minus X, right? Whatever X is, if I subtract those, that would give me how many moles of carbon monoxide are left. For my hydrogen, I have 3.000 moles minus 3X. Whatever X is, times it by 3, subtract that from 3, gives me how many moles. And of course, I'm left with just X amount of moles there and X amount of moles for both of my products. However, the problem does say that this mixture is found to contain 0.387 moles of water. So we must know that X is equal to 0.387 moles right here. So if 0.387 is equal to X number of water, that must mean that I'm producing the same amount of methane, right? Because it's a 1-to-1 mole ratio. And I can easily figure out how much carbon monoxide is there because if X is equal to 0.387, 1 minus 0.387 gives me 0.613 moles. And then for here, 3 minus 3X gives me a value. If I plug in that value for X, I get 1.839 moles. This is how you can use an ice chart to determine how many moles or what's the concentration of some equilibrium composition, right? If I have these starting materials and I know that balanced chemical equation, I could figure out what is the final concentration or the final molar composition of each reactant and product in that particular scenario. And we could do that using an ice chart right here. My students usually hate ice charts. I don't know why. Hopefully this semester we do a lot of them that you won't hate them as much. Let's try sample problem 10 in this case. So we're taking this idea of the ice chart and really putting it together with a lot of stuff we've already learned. So in this case, it's saying, let's see, a flask initially contained hydrogen sulfide at a pressure of 5 atmospheres at 313 Kelvin. When the reaction reached equilibrium, the partial pressure of sulfur vapor was 0.15. So this is 0.15 at equilibrium. Whereas a flask initially, that's important. This is before equilibrium. Okay, so I put in hydrogen sulfide until it had a pressure of 5 atmospheres, let it react, and I found out that the partial pressure of sulfur vapor was 0.15 at equilibrium. We want to know the value of Kp for this reaction. So let's go ahead and set up an ice chart. 2H2S is in equilibrium with 2S2 and some S2. So I have ice right here. My initial amount of hydrogen sulfide is 5 atmospheres. And I had no hydrogen and I had no sulfur. Did I draw that 2 backwards? What the heck am I doing? There we go. So I started off with 5 atmospheres of H2S and I had no hydrogen and no sulfur. However, this is allowed to react and I'm going to produce products because I have to in order to achieve some sort of equilibrium. So these 2 values, the change has to be positive. whereas this value is going to have to be negative. I'm using up some of that hydrogen sulfide. However, I don't know how much I'm using up, but I do know the general ratios. Sulfur, I'm producing so much of it. I'm just going to leave it as X. However, I'm producing double the amount of hydrogen because that has a coefficient of 2 in front of it. And in the same rate, I would be using up 2 times the amount of as much as S is produced because of that balanced chemical equation. So all I'm getting those numbers from are from that balanced chemical equation. My equilibrium values would be, so I have to kind of combine these two right here. So my equilibrium pressure would be 5 minus 2x. I would have just 2x as the pressure for hydrogen and x as the pressure for sulfur. Just like before, though, it is saying that the partial pressure of sulfur vapor at equilibrium was found to be 0.15. So I know that X must be equal to 0.15 atmospheres. If I know that this is 0.15, my partial pressure of hydrogen would be double that, and that's because that has the coefficient of 2. So I would have 0.30 atmospheres. And then if I take 2x, that's 0.3. 5 minus 0.3 gives me a partial pressure of 4.7. Make it 4.70 atmospheres. So I do still have a very high pressure of my reactant. And this can start to tell you how your value of K should be. Should it be a high value of K or a very low value for K? Well, if I have a high concentration of reactants, that must mean my denominator must be very high relative to the numerator, which means K would be very low. So it is asking us here, what's Kp? So I do know my expression is equal to partial pressure of hydrogen squared times the partial pressure of sulfur over partial pressure of hydrogen sulfide squared. Okay, so that's just a general equilibrium expression. I can now plug in these partial pressures in order to get the value for Kp. So my H2 is 0.30. I'm going to square that. Times my partial pressure for sulfur, which is 0.15. And I'm going to put that over right here, my 4.7, which is squared. I'm not putting units in here just to make our life a little bit easier. And we should, in fact, see that we get a very small value. It's 6.11 times 10 to the negative 4th. So knowing a little bit of information about an equilibrium, we can determine an equilibrium constant based on that information. So we did figure out the equilibrium constant there. As you could see, not really rocket science, not that difficult to do, just takes a little bit of practice, just like everything we've been doing at this point. Let's take a look at sample problem 11. So at a certain temperature, a 1 liter flask initially contained 0.298 moles of PCl3 and 8.70 times 10 to the third moles of 10 to the negative third, moles of PCl5. After the system had reached equilibrium, 2.00 times 10 to the negative third moles of chlorine was found in the flask. There's the reaction right there. Calculate equilibrium concentrations of all species and the value of K. So let's write out in our equation here. Equilibrium with PCl3 and Cl2. Set up an ice chart. A lot of students will ask me, is there another way to do it other than the ice chart? No, there's not. So don't even ask me. This is the way to do it. Let's see. 1 liter flask, it does say equilibrium concentrations. So luckily I take moles divided by 1 liter. That is the concentration. So I don't have to do anything specific. Let's see. Starting off with 0.298 molar PCl3. 0.298 molar PCl3. And I have 8.7 times 10 to the negative third PCl5. 8.70 times 10 to the negative third molar. This is not at equilibrium because, as you see, I do not have any chlorine that's produced here. And in order to have equilibrium, I have to have some amount of everything that's there. Because this chlorine is starting off at a concentration of 0, I know that we must be shifting towards the product side. I have to make some chlorine in this case. So my change in concentration would be positive for the products because I have to make more Cl2. In order to make Cl2, I have to also make more PCl3 because PCl5 is what's going to decompose. So my change is going to be negative X in this case. And because it's all a 1-to-1 mole ratio, it's all the same value. Equilibrium concentrations would be 8.7 times 10 to the negative third minus X, 0.298 plus X, and Cl2 is just X there. It does tell me how much chlorine was found in the flask after it had reached equilibrium. So I do know what X is equal to. X is equal to 2.00 times 10 to the negative third. And if I know that X is equal to that value, I can then calculate, well, what's the equilibrium concentration for these two as well? This guy is going to be 0.3. Should be a decimal point in there. And this guy is going to be 0.0067. This is molar concentration. Now that I have each of those equilibrium concentrations, I could plug all of these into my equilibrium expression and to get the equilibrium constant. So I know that Cl2 times PCl3 over PCl5 is going to give me my equilibrium constant. So let's do 2.00 times 10 to the negative third times 0.3 over 0.0067. And when we do that, we get 8.96 times 10 to the negative second. Still pretty reactant heavy at equilibrium. I do have quite a bit more reactants there relative to products. Let's try one more together. This is a good one. So it says chloromethane, which has been used as a refrigerant and a local anesthetic, can be made from the following reaction, which is given to us there. If enough methanol and hydrogen chloride are added to a container to yield an initial pressure of 0.75 atmospheres for each reactant, this should say for each reactant. Each reactant. It's not very clear what it's asking for. Then it should say, what will the equilibrium pressures of all the reactants and products be? Okay. So start off by writing our equation. I like to rewrite this here so I have it nice and big. See more what I'm doing. Don't try to jam stuff all into one spot. Set up an ice chart. And I'm starting off with 0.75 atmospheres of both reactants and products. Notice how I started off with pressure, and then I went to concentration, and now I'm back to pressure. Ultimately, it doesn't matter. It's all the same work, right? You would just calculate Kp, or you would calculate Kc. I believe I did tell you there is a conversion on how to convert Kp to Kc, but you don't need to know how to do that, so don't worry about it. But as you can see, we can interchange each of these pretty easily. I have to go in the forward direction because I have no product. So my initial concentration is 0 for each of those. So therefore, I'm going to produce some amount of each of these. The mole ratio is, or the pressure is going to be the same for them because they're both 1-to-1. And these two are getting used up the same amount because they're a 1-to-1 ratio. So if I wanted to know my equilibrium pressure, I have 0.75 minus X, which is the same for this one, X and X right there. However, the question is asking, what will be the equilibrium pressures of all the reactants and products? Now, in this case, rather than solving for Kp, we're given the Kp in this case. And notice this Kp is relatively high, so it should have a high concentration of products. However, we have to use this and set this up and solve for X, because that's what we're trying to find. What is the equilibrium pressures of all reactants and products? So let's see, Kp, which is 5.9 times 10 to the positive third, that's equal to X times X over 0.75 minus X times 0.75 minus X. What in the world? There's a lot of stuff going on here, okay? How do we solve this problem? Well, if you look closely, you could see that X times X on top would give you X squared, right? And actually on the bottom, I have 0.75 minus X times itself. So that's also 0.75 minus X squared. So if I were to solve this appropriately, the best way to go about this would be to take the square root of both sides, like that. There are more difficult ways of doing this. Like I said, you could solve this. You'd have to probably use the quadratic formula. Sometimes you might have to do that. I will give you an online calculator you can use to do that. I'm going to try to eliminate that, though, this year as best as I can. No promises. But this is a perfect square, which makes life a little bit easier. So if I solve for this, the square root of this value is 76.8. And that's equal to X over 0.75 minus X. Okay. And now it's much easier to solve for X now that I got rid of that square. So if you correctly find the value for X, you should get 0.740 atmospheres. However, that's not giving us the answer, because the answer is asking us for what will the equilibrium pressures be for all the reactants and products. So we know that the pressures have to be the same for the products, and that's because they have the same coefficient. So my partial pressure of H2O and my partial pressure of chloromethane is going to be 0.74 for each of them. And that's because that's equal to X. However, my partial pressure of methanol and my partial pressure of hydrochloric acid must be 0.75 minus 0.74. So that gives me 0.01 atmospheres for each of those. Notice how this correlates with the value of the equilibrium constant. We already said this equilibrium constant is very high, which means I should have a very high concentration of products. And you could see I do. My concentration of products is very high relative to my concentration of reactants. It's always good to go back and double check to make sure, does my work make sense based off of what I already know? And in this case, it does. We're going to do a lot of practice with ice charts in class, so please don't fret. This is just the beginning. But of course, if you have any questions, feel free to ask me, take some notes in your packet. And otherwise, I will see you in the next video, which gets exciting. We're going to talk about good old Le Chatelier and his principle, what happens when we add a stress to a system. And I will see you then. Bye.